Okay. So, in the previous class what we have tried is we were trying to actually get a methodology or propose a methodology where we can actually compare in terms of noise analysis different modulation scheme. So, we already proposed one where we have told that okay, we will take baseband transmission and we will take the corresponding modulated transmission, and for this purpose we will try to equate these two power. Baseband whatever power we are transmitting, we should be also transmitting the same power at the modulated part. So, basically our methodology was for the modulated first calculate the power, same power you put in the baseband, okay. And then baseband we could evaluate, because baseband whenever you transmit at the receiver side it is very easy, it is just a low pass filter, noise will be added in the channel and low pass filter. So, we could actually evaluate the SNR, signal to noise ratio, and we call that means reference SNR, okay. And then for the modulated we have actually done the entire modulation process. For DSB-SC we have already analyzed it, we have told that we have in the receiver front end we have a band pass filter, that is of course for rejection of noise, followed by the entire demodulation, okay. So, after doing that entire demodulation we just have taken one help of this noise representation, which is the band pass noise representation, okay, or band limited noise representation. So, that particular in phase and quadrature we have written. After doing the entire demodulation process, we could see that my ultimate output of a DSB-SC signal should be this. This is something we have already proven, okay. So, now let us try to see how do we calculate the signal power. So, the signal power must be coming from this. See, MT gives me a power of P, and that is multiplied by C, AC and half. So, power spectral density, if we just go and then integrate, I should be getting 1/4 C square, AC square and P, right. So, that must be the signal power after demodulation. Now, I have to get the noise power, so that should be this power, okay, which is nothing but 1/4, because there is a half, and the integration of power spectral density of Ni. This is something we have already characterized in our band pass random process analysis. So, we have told that if I have a corresponding N which is going from that center frequency minus Fc plus Fc, and this band is 2W. We have told this Ni or Nq will be nothing but this shifted to this side plus this shifted to this side, okay. So, if this strength was eta 0 by 2, both of them will be shifted and the overall strength will be eta 0 or N 0. So, this should be N 0 defined from minus W to plus W, right. So, that is my Ni or the power spectral density of Ni, S Ni F. So, what is the overall noise power then? It is just the integration of the power spectral density. So, that must be N 0 into 2W, right. So, that is my noise power. There is a factor of 1 by 4. So, it should be 1 by 4 into N 0 2W. So, that is actual. So, this if I write as this, so that is actual noise power, right. So, what is my signal to noise ratio for this modulated scheme? So, if I just say SNR for this DSB SC, that must be this power 1 by 4 C square AC square P divided by this noise power, which is nothing but half N 0 W. So, that 2 gets cancelled, I get C square AC square P divided by 2 N 0 W. So, that is the SNR for DSB-SC. if you just go back and try to check, the reference SNR was exactly the same. Okay, the expression was exactly the same. So, therefore, the figure of merit must be 1, must be this SNR for DSB-SC divided by SNR of the reference, because they are exactly the same. So, it should be 1. So, for DSB-SC, in presence of noise, it gives me no degradation or no advantage compared to baseband transmission. This is something we have understood. Whatever the SNR I get when I do baseband transmission with the same amount of power, if I transmit, whatever advantage I will be getting, DSB-SC does not give me any degradation or any advantage. Okay. So, this is something we have now figured out for DSB-SC, that is something which happens. Okay. So, next what we will try to do is, we will try to see if the AM version of it, where you do not suppress the carrier, is it having similar thing, okay, or is it something else. Then only we will be able to compare whether noise performance wise these two modulation schemes are equivalent or one has some advantage over the other. Okay. So, let us try to do the noise analysis. Of amplitude modulation. Process will be same. So, the process must have a baseband equivalent transmission, which we have already seen, okay. And there should be a modulation. Now, the modulation, our signal is something like this, we already know this. Okay. So, where this Ka is related to the modulation index, we have defined this when we did our AM, and this is the amplitude of the carrier signal. Okay. So, basically what we do, nothing but we actually add a DC to the signal and then modulate or do a DSB-SC, or otherwise in a way you can see it as the DSB-SC plus the carrier part. If you just multiply this, that should be the carrier part. So, the carrier has been also added over here. So, this is our modulation. Corresponding demodulation, the demodulation of AM was easier. What we did is something like this. You have this ST plus noise, which is let us say WT, coming through the channel. At the receiver, what you do? You first put, any receiver will have band pass filter, that is guaranteed, because you want to reject the noise as much you want. If it is a low pass signal, you will have a low pass filter. If it is a band, means signal having some bandwidth at a particular band, then you have to put a band pass filter. So, you put a band pass filter followed by just envelope detection. This was our amplitude demodulation, right. So, we will not change that circuitry. So, that must be our YT. Okay. So, let us now try to see what kind of power we are now putting. First of all, see, anywhere the techniques are same, we need to launch same power for the baseband transmission as well as the modulated transmission. Okay. So, that is why, because the modulated transmission is little bit complicated to calculate, first we will calculate the modulated transmission power, and that same power we will put in the baseband. Earlier also we have done the same thing. So, here also we will do the same thing. So, what is the power that is launched whenever we do this modulation? Okay. So, the power that will be launched, see this AC cos omega Ct, that is a cosinusoidal signal with amplitude AC. We know that the power of that is AC square by 2, right. This is something we have already done. So, that must be AC square divided by 2 plus this AC into Ka, that is already there, right. So, earlier also we had done this C into AC, right. So, instead of C it is Ka. So, that must be SE square into Ka, and this MT, if that has a power of P, then it should be, because it is multiplied by cos, so it should be P by 2. So, I can write as AC square Ka square P divided by 2. This is the power, if I modulate, will be launched. So, what I have to do? I have to equate the power. So, therefore, this is the power I will be also putting in the baseband. So, baseband power is this. What is the baseband noise? That is equivalent to the previous case, because it is just N0 by 2 from minus W to plus W. So, overall power, noise power is N0 by 2 into 2W, which is N0 into W. So, therefore, our SNR reference must be this divided by this. So, it must be SE square, that gets common, 1 plus Ka square P divided by 2 N0 W, right. So, that is the reference SNR that we get. Now, we have to do the envelope detection. Okay. So, we will again employ the same thing. So, I have this signal plus noise, which should be passed through a band pass filter. This band pass filter, because it exactly matches with the band of this one. So, ST will remain intact, the noise will be passing through the band pass filter. So, it will have a equivalent band pass representation, okay, with in phase and quadrature. So, therefore, that after the band pass filter, if I call that signal as Vt, that must be our AC plus AC Ka Mt cos 2 pi Fct, right. So, this is the message signal or modulated signal plus Nit cos 2 pi Fct plus Nqt sin 2 pi Fct, just the noise gets a in phase quadrature representation, right. Now, next what will happen? This particular Vt will go through a envelope detection. That means, whatever I have, this is a sinusoidal, or this can be termed as a sinusoidal, its envelope will be tracked. So, all I have to do is, I have to now see what is the envelope of this one, which has a frequency of Fc, because this has this carrier which has a very high frequency. So, it is actually the underlying frequency term is this cos omega Ct, we just need to see the envelope of that. Okay. So, there is a cos term and there is a sin term. We know how to calculate the envelope, that should be the coefficient of cos square plus coefficient of sin square root, that must be the envelope. We have already derived this part. Okay. So, let us see what is the coefficient of cos. Coefficient of cos is AC Ka Mt plus Nit, right. So, that is the coefficient of cos. So, this square plus coefficient of sin is sin 2 pi Fc is Nq. So, Nqt square, I need to take a square root of that. That must be the envelope. So, this is my Yt then, because the envelope detector will exactly detect the envelope of this carrier. Okay. So, that must be my overall envelope. Now, we will insert something, okay, because this is a complex this one. Now, you can see the noise, square root, all kinds of things has come. Okay. So, it is no longer a very nice linear thing like we have assumed or we could see for the DSBSC. So, it is going to be harder to analyze, okay. But we will take a very simplified assumption over here. We will say that this noise term, generally that should be the case, this Ni, both Ni or Nq, which is the in phase or quadrature component, that must be much less than this AC. Okay. So, this is one assumption we are taking. With that assumption, generally you will have to put a high carrier. So, if you are doing that, means as long as this is valid, you can do some analysis. So, let us try to see what that will be. So, immediately yt I can write, see we have this square plus this square, this particular term has AC square. So, this will be much lesser compared to this particular part, okay, because this is already lesser, then square of that will be much lesser. So, I can neglect that part. So, immediately if I neglect, what will I have? I will have a square and a square root that will cancel out each other. So, I will get this AC plus AC Ka mt plus NIT. So, again we get back similar things, where this is probably the signal part and this is the noise part. This is the DC part. We have already seen that after envelope detection generally you will be having a DC blocker which will block this part. So, this will be already gone. We will have just this power and this power. So, now we have to again evaluate the signal to noise ratio. Okay. The signal power is how much? It is actually AC square Ka square into P by 2. So, that is the signal power, and the noise power is this Ni whatever that is. Okay. So, Ni we have already evaluated that must be with strength eta 0 going from minus W to plus W. So, that must be 2 N0 W, right. So, this if I put, I will be getting SE square K square, oh sorry, this 2 why I have put, there should not be any 2 because there is no modulation term, it is just directly empty. So, it should be this P divided by 2 and 0 W, right. So, that is the SNR of AM. Now, if we wish to calculate the overall figure of merit. Okay. So, figure of merit of this modulation. So, figure of merit will be, first we have to put the SNR of AM divided by SNR of the reference. SNR of AM we have got AC square Ka square P divided by 2 N0 W, and SNR reference we have got as, what was it, AC square 1 plus Ka square P divided by 2 N0 into W. AC square gets cancelled, 2 N0 W gets cancelled. So, you are left with Ka square P divided by 1 plus Ka square P, right, which is for sure less than 1, because I already have a Ka square P, I have something added to it. So, definitely I know the figure of merit of this one is less than 1. Okay. So, what does that means? That actually says that after doing this analysis we could understand that probably DSB-SC is better noise resilient compared to AM, because AM to get similar amount of signal to noise ratio will have to launch a huge amount of power, okay, because that carrier power we are putting, that is wasted, and that is not really giving me any help in terms of noise cancellation, right. It is not boosting the signal power, which will be the actual signal power that will be demodulated. So, because of that we have a degraded signal to noise ratio performance. Okay. So, if we just give one example probably. So, if we take our MT to be some AM, just a tone modulation. Okay. So, if we just take that, So, mt is also a sinusoidal. So, basically we are modulating a slow varying sinusoidal with a faster varying sinusoidal, which we have also done for demonstration purpose, right. So, this is usual practice, we just want to see what happens. Okay. And let us say our modulation index in that case is something like this, 1 plus mu So, this is the modulation we employ, mu is the modulation index. Okay. So, if this is the case, now what is mu? That is actually Ka into Am, I can write it this way. Okay. And my power is half Am square because it is a sinusoidal. So, the power should be amplitude square divided by 2, right. So, this is my overall power. Okay. So, therefore, the figure of merit that we have already calculated, that is Ka square p divided by 1 plus Ka square p, which if we just put, so Ka, okay, we can put it in terms of mu. So, Ka square p, if I just put half Am square, so I get Ka Am square divided by 2, 1 plus Ka square Am square divided by 2, that is nothing but this is actually mu square by 2 plus 1 plus mu square by 2, or I can write it as mu square 2 plus mu square. What is the highest value of mu that I can take? 1. We have already seen that for proper Am modulation, so that we have enough DC shifted and it does not do any zero crossing. So, to do that, so that envelope detection is proper, we need to maximum mu I can take is 1. So, if I just put that maximum mu, I can immediately get figure of merit to be 1/3. So, that is the maximum I can achieve. So, it will be whatever happens for a tone modulation, we can already show that this is the best figure of merit we can get. It can become even worse than this, this is the best we can get. So, this is 1/3 time worse than the corresponding DSBSC modulation. Okay. So, that is something we wanted to say, that now with the noise analysis we can actually insert that, okay, one of them is better and the other one is probably not that better. Okay. What we will do next is, means similarly we can start doing analysis for everything. I will just demonstrate one of them because it is little more critical. So, that is why I will demonstrate the other one, which is the SSB. Okay. So, single sideband, of course, suppressed carrier. So, this is something I will try to demonstrate next, and what we will try to do is, this will almost give us most of the tools that are required while doing this analysis. If you wish to do for VSB, it is almost similar, only thing is that for the filtering you will have to take a proper care of that, because VSB has a different kind of filtering, it is no longer a sharp filtering. Okay. So, accordingly the noise and all those things will be accordingly adjusted, you will have to do that. Okay. So, I will not demonstrate the VSB part, but probably the SSB I will demonstrate, because you will see something something more critical will come up with the noise processing. Okay. So, for SSB, what we need to do is again the similar thing. Okay. So, we have to actually define a signal for SSB, which is nothing but mt cos 2 pi fct plus mht sin 2 pi fct. This can be plus or minus depending on upper sideband or lower sideband which we are transmitting. Okay. And MHT is something we know already, it is the Hilbert transform of our signal, right. So, this is something we already know. So, the characterization of that is, if we write the frequency response of MHT is MFT, or we should not say frequency response, it is the frequency representation of that or amplitude spectrum of that. So, that is the MHF, that must be, we already know, that should be J MF signum f. This is something we have already defined, which is nothing but plus minus J MF if f is greater than 0, or plus J MF if f is less than 0, right. One of them you can make equal. Okay. So, this is something we already know. Why we are telling all these things? Because we will have to finally calculate the power. To evaluate the power, I only know the power of this MT. MHT I have to now calculate, okay, what is the corresponding power of that, because otherwise I will not be able to evaluate the overall power that will be transmitted, right. Because whenever I transmit a modulated signal, I have to first get the power, and that power I will be putting in the baseband. So, that is something we have to first characterize. Okay. So, to evaluate the power, let us try to see how do we do that. We know that MT has a corresponding Fourier transform as MF, and it has a corresponding power spectral density which is SMF, right. And we also know that minus W to, it is a band limited signal, and minus W to plus W SMF, this is something we are keep on telling that this is P, that is something we know. Okay. Now, let us try to see what will happen to MH. So, immediately we have already told that MHT, that must have a Fourier transform which is MHF, okay, which looks like this. Now, let us go to the power spectral density. Okay. So, whenever you will be evaluating power spectral density, it is the modulus of this square. You do the modulus, this plus j or minus j has no effect. So, you know that the power spectral density, whatever happens, it will be equivalent to whatever we get through MF. Okay. So, both the power spectral density will be equivalent. Their amplitude spectrum, or I should say means amplitude and phase spectrum, especially the phase spectrum will be different. Amplitude spectrum will still remain the same, only the phase spectrum will be different. But if I go to power spectral density, they have exactly no difference. Okay. So, therefore, for this one also, if I just write that as SMHF, so that also I can insert that is band limited, and minus W to W if I integrate, that must be also P. This is the extra information I get. Okay. So, what we will try to do in the next class is, taking these two information, we will try to first evaluate the power of this, okay, and then we will try to see what is the corresponding overall noise analysis can be. Okay. Thank you.